Today we will be starting a new session on the course Line Commutated and PWM Rectifiers.
So let us now analyze the switching state 1 in details. Okay. So let us see the positive half cycle of the AC waveform, and here you can see the circuit. Okay, the diodes D1 and D4, have been turned on here. Have turned on, and therefore the voltage VG has come across the inductor. And in this switching state 1, as we have mentioned before, we have turned on the MOSFET. Since the capacitor voltage, the V voltage at the output, the capacitor voltage here, this voltage is more than the input voltage, instantaneous input voltage. Therefore, the diode will be reverse biased, and therefore the diode will not conduct during this time. And this time we are defining as t equal to 0 to t equal to d times ts. D is the instantaneous duty at this cycle. Now, this dTs time period, as we mentioned before, the Ts time period can be 10 microsecond. So dTs time period is even smaller than that. And in this small time period, we may assume that the input and output voltage of the boost converter may be considered constant, right? Because the input voltage Vg is part of a 50 hertz or 60 hertz sine wave, and therefore this Vg is it does not change much during the time when this 10 microsecond period. On a similar argument, we can also say that this portion here, the output voltage, in the output voltage also, we will not have much change, because the capacitor is adequately designed so that there is no loss of voltage. The capacitor is fairly large. Okay. So therefore, the output voltage is constant and the input voltage is constant. Okay. So during this time, inductor L is charged, right? And since Vt is, so the load is now powered from the capacitor. So which also shows that this means that this capacitor is now discharging through this load during this time. The inductor is charging and the capacitor is discharging. Okay. Now, during this time, what are the governing equations? This exactly follows the way we analyze the boost converter. So, like you have VL is equal to L di dt is equal to VGT, okay, because the inductor voltage across inductor is VGT, and this is shown here in this waveform. Okay, VL is equal to VGT. Okay, instantaneous grid voltage. Okay, the VG is continuously varying in a 50 hertz cycle. So this causes of course the VGT is positive, and therefore the inductor current will rise here, L di dt. If we look into the capacitor current, okay, the capacitor current is this current, which is ICT. Okay, the capacitor current here is equal to minus V by RL, and this capacitor is basically discharging. Okay, so therefore the current, we can assume that V is constant during this time. Actually, it is basically an RC circuit, and the current will exponentially change, but within that small 10 microsecond period, the exponential curve can be approximated as a straight line, and therefore we have denoted it by this minus V by RL. Okay, so some mathematical manipulation so as to get delta IL, I mean the change in the current. So what is delta IL? Delta IL is this change in the current. Okay, this is the delta IL. Okay, this change in the current can be also, so we can rewrite equation 5 as something like this, and therefore delta IL can be VGT into DT into TS divided by L. Okay, as I have repeatedly pointing out, VGT and DT are varying. Okay, now we also know that in a boost converter, the relationship between output and input voltage is V, capital V is the output voltage, and VGT is equal to 1 by 1 minus D. Okay, this equation here in equation 8, right? We already know this one, right? So, um, by doing this exercise, what we can see here is, um, yeah, now let us do the switching state 2. Okay, let us do the analysis of the switching state 2 and find out what are the governing equations. What happens during switching state 2 is that still D1 and D4 are forward biased. It is the same positive AC half cycle, but now we have turned off the MOSFET here. As soon as we turn off the MOSFET, the diode DPFC will immediately get forward biased because of the current that is flowing through the inductor. Okay, and so it will get forward biased, and then the capacitor C is now getting connected to the grid voltage. And since the capacitor is voltage is more than the grid voltage, now the inductor will actually discharge. Okay. So what is the voltage that comes across the inductor during this time? The voltage across the inductor is given by Vg minus V. And since Vg is less than V, this value is negative. Okay. And this also is consistent with what we know as the volt-second principle in an inductor voltage, on the inductor voltage, for the volt-second principle, which we study in conventional DC-DC converter. So we had given a positive voltage and in the first half cycle, and we have given a negative voltage in the second 1 minus d Ts time period. And so if this voltage comes across this one, then we can also write that the inductor current will fall, right? Because now LDIDT is negative, right? Now, looking into the capacitor part, okay. If you look into the capacitance side, so then now the capacitor will be basically charging up, okay, from the AC side. Remember, in the previous uh, DTS time period, the capacitor was discharged. Now it must charge up, okay? Only then it will attain a steady DC voltage, because it has to charge and discharge every alternate periods in the switching cycle. Every DTS and 1 minus DTS time period, it must charge and discharge like the inductor. So the capacitor will now charge up. And how will it charge up? Because now we have this voltage, which we have this AC voltage, input AC voltage connected to this capacitor. And so the current which will flow through the capacitor now will be this IL current, okay, and the rest of the current, so V by RL will flow here, okay. V by RL, this current will flow in this load, whereas the rest of the current remaining from the inductor, that flows through the capacitor here. Okay, so that is what we have written here at the bottom. IC is equal to IL minus V by RL, right? And this current is positive. Last time the current was negative. And so therefore, this current will cause the capacitor voltage to increase. Okay. So therefore, the continuous charge and discharge of the capacitance or the capacitor will happen. Okay. And these are the equations which are given here. Okay. Now, since we have understood these equations fairly good now, we can now apply the same concept when we are dealing with the switching states 3 and 4. Okay. Remember that or recall that in switching state 3, we had the negative half of the AC cycle. And in this case, D2 and D3 were turned on. But what comes here, the VG voltage is exactly the same as before. Okay, the VG voltage here is exactly the same voltage as before. And now we have again the same thing which is repeating in switching states 1 and 2. We have the same relationships happening, right? So once the MOSFET will turn on and it will follow the same. So switching state 3 is identical to switching state 1 analysis, and switching state 4 analysis is identical to the switching state 2 analysis, right? So therefore, we can say that the same relations can again be written for the negative half of the AC cycle. Okay, so this is fairly straightforward. Now, so this gives us a mathematical framework of analyzing the or some expressions which we have derived. Now, there is one more thing that we have to also understand is what is called as CCM and critical conduction mode and DCM operation. Okay, so the boost converter. So if you see the uh, boost converter, traditional DC-DC boost converter, you can understand that it can run in CCM or DCM or even critical conduction mode, CRCM. Okay, CRCM is critical conduction mode, and uh, here CCM means continuous conduction mode, and DCM means discontinuous conduction mode. Okay, so the boost converter can run in all these modes of operation. So when you so if you can just quickly a little bit recap what is CCM, what is CRCM, and what is DCM. So if we see the inductor current, okay, if so the inductor current is usually something like this in any DC-DC converter. Okay, so this is in IL and this is time here. Okay, inductor current. So in CCM, what happens is that the lower value of this of the inductor, the lower value of the current, okay, in the inductor does not touch zero. Okay, so this is called CCM operation. It never touches zero. Of course, the upper value is always more than the lower value. So the lower value does not touch zero. What it means, basically, if you can see that the inductor is charging and discharging in every cycle, right? When the current, if the current value goes to zero, then that means the total stored energy in the core of the inductor, okay, the energy stored in the core of the inductor goes to zero, because the energy stored in an inductor is half Li square. So if I is zero, then the total energy stored in the inductor is completely discharged. Okay. In CCM, as you can see from the curve, in CCM, the current here is not going to zero, which means we have some stored energy in the inductor. The stored energy is fluctuating, okay, because the current is increasing and decreasing, but the stored energy in the inductor is never touching zero. Okay, so it has always some buffered energy. Now let us, this is what is known as the CCM. Now if you can see what is critical conduction mode. Critical conduction mode is something where the inductor current, as I am showing it now, this is touching 0. Okay, this here it is touching 0. This is called a critical conduction mode. Okay, right. So when it is here, then what is happening here is that the inductor energy is 0 at the end of the cycle. Okay, of the switching cycle. It starts from 0, it gains some energy, but then releases that energy into the capacitor or someone else in the circuit. So what is the difference? In this case, what happens here is that you have actually given the inductor certain energy, but you have withdrawn all the energy from the core of the inductor at the end of the cycle. Okay, so it so this is what is happening in the critical conduction mode. And then there is something called as DCM. Okay, what is DCM? DCM is the case where this current, okay, this current goes to some value here, but it comes to 0 even before the end of the cycle. Okay, so this is, and then again it remains 0 for some time, and then again it starts, and then again goes down. Okay, it's like this. Okay, so there is a prolonged time period here, which I'm showing here, where the current is discontinuous. Okay, so it is a discontinuous mode. So current is 0 for a prolonged time. So this operation is sometimes used because, as we will see here also, the size of the inductor goes down, okay, in DCM. The reason is basically you are not storing so much of energy in the inductor. Okay, so the size of the inductor can go down in DCM operation as compared to CCM operation. Okay, because but there is something also, there is going to be one challenge here. Okay, we will see this challenge, what will happen here. Okay, you will see that the peak current will increase, although if you go into, we will see this one. But you can see that in the operation of CCM, critical conduction mode, and DCM operation in terms of the inductor current. Okay, now if you suppose the analysis with the CCM boost converter is most straightforward, and we'll start with that. Okay, so when the boost converter is operating in CCM, okay, so what we will get, okay, so this is the most common operation. So then dt is equal to, from 8, we have defined already the 8, 8 means, just go back, 8 is this equation at the bottom, the output and input voltage relation, 1 by 1 minus t, this relationship. So from 8, we can write dt as 1 minus vgt by capital V. Okay. Now, as I told you, we are operating in the CCM mode. So in this case, the waveform of the current will be something like this. It is not touching 0. So which means the average value of the inductor current will be somewhere here. So this is the average value of the inductor current, IL average. Okay, this is there here. Now, obviously, because we are not touching to 0, it means that the delta IL by 2 should be less than the average grid current, because this is delta IL here. Okay, so this delta IL by 2 must be less than the average grid current, right? Otherwise, it will touch 0 here. Okay, so therefore, we can say that delta IL by 2 which we have already seen from the previous slide. The expression of delta IL by 2 is this one, VGT dt dTs divided by 2L. That must be less than the average inductor current. Now, what is the average inductor current in one switching cycle? The average inductor current is nothing but the grid current. Okay, and the grid current is VGT by RE, where RE is the equivalent or emulated resistance. Now you see how that emulated resistance we will repeatedly use in our analysis. Okay, because if we make this perfect PFC boost, the grid current, we can always write or we can always model the grid current as VGT divided by RE. Okay, because we know that the the boost converter or the PFC boost converter is behaving like a perfect resistor. So we can always write the grid current as VGT divided by RE. Now this, but note that this VGT is varying in time. So the average grid current is varying in every switching cycle, like 10 microsecond. It is continuously changing. So basically we are, again, I will want to emphasize this. This is IGT and we are looking into a small window here. Okay, we are looking into a very small window of 10 microsecond, and in that we are analyzing the whole thing, right? So delta IL by 2 is equal to this VGT dt TS divided by 12, which must be less than VGT by RE. So if you manipulate this equation a little bit, so you take this thing up and down, and then you will see that dt, the instantaneous duty ratio, must be less than 12 by RETS, okay, to ensure that the boost converter is in CCM operation. Okay. So yeah, so this is what we have seen. So now we are trying to find out a condition where this, so this is dt is less than 12 by RTS, and hence we can always say that, again, manipulate the equation, take the RE on the numerator. So RE must be 12 2L divided by DTS. So this factor here is d of t. Okay, so D is 1 minus VGT divided by capital V. So therefore, RE is less than 12 by this one. This is the equation. Now what there is something interesting here. Now we have now plotted this inductor current, okay, and we have shown you two zoomed portions. Okay, let me change the color. Okay. So you can see here, first of all, let us concentrate on this part. So this is the 50 hertz cycle. So this is like 10 milliseconds here. Okay. Okay. And in which we are looking into two small zoomed portion. Now, if you look into this zoom area, okay, if you zoom in into this, the inductor current is something like this. Okay. Which is obvious. We have already analyzed how it works. But now if you zoom in to this portion, which is close to zero, okay, this portion is interesting. It is interesting because of the fact that uh, here the inductor current is basically starting from zero, and there may be some cycles during this time, okay, where we will not be uh, able to maintain this condition, or the inductor current will slowly rise, and therefore it may go into a DCM or critical conduction mode. Okay, this will happen particularly when the current is zero, because of the simple fact that the inductor current initially will, the average value is less, right? The IGT average value is less when you are near the zero, and the IGT average value is more when you are at the peak of the AC. So initially it will happen like this, it will go like come to DCM, then it will move slightly more, slightly more, and then critical conduction mode, and then it starts to move into CCM. Right? So this is how the transition is happening, which is shown here. Okay, which is shown here. You can see here what we have done. Okay, initially the current is 0, and then it rises a little bit, but the average value of the current is less near the 0 crossing of the AC cycle. So we may go into DCM, then slowly it goes into critical conduction mode, and then slowly it comes out of critical conduction mode, and then then it goes into full CCM. Okay, so that is why let me now erase this portion and oops, uh, try to erase this portion. Okay, so now this means that now we have understood that uh, this equation, okay, that 13 is satisfied during some parts of the AC cycle of the VGT near the peak values of the AC waveform. Okay, but near to the lower values, in particular near the 0 of AC, 13 may not be always satisfied. So we may go into DCM or critical conduction mode. Okay, so this means that the converter is working at CCM near the peak, but works at DCM near the 0. Now, one thing that I also would like to mention, and please note that uh, this value of the current, this value of the current can vary. Okay, so basically so what decides this value of the current? Um, it depends on how much is the total converter is loaded at the output. So initially at the beginning of the lecture, I said that suppose you are feeding this to a server power supply. The total power consumed by the server will vary, okay? Because if there are the processing on the server is very high at certain points of time of the day, then the power consumption will be higher. But it may go into a sleep mode or hibernation mode, or not like that, but it may go to a low power mode if the processing needed from the server is low at some other points of time. So which means, therefore, the power supply to this server, right? The power supply will feed different levels of power to the load. And so therefore, this current, okay, this current may be like this with suppose I just give you an example with an 10 ampere at some point of the day, but it can be with again a band of current with a value of say 2 ampere here at some other points of the day, right? Now so this means that the uh, this means that this statement, okay, where we have the zero, the VGT near zero, that is yeah, near the zero. So that region, okay, will change over time because the load is itself changing. So we may have more region where this is operating in critical conduction mode and then goes into CCM when the current value is high. Okay, so the region at which this region near the zero, this region may actually vary with loading. Okay, this you must understand, because if the average or the average value of the current itself is small, these two cases which I was discussing, 2 ampere and 10 ampere, then that region where CCM is not happening, that region near the zero crossing, that region may also alter. Okay, so this is something which we must keep in mind. Okay. Yes, so this is also what I wanted to convey. Here you see from 12, maximum value of dt is, so RE is less than 12 by TS. Okay, this ensures CCM throughout the AC cycle. Okay, if you go back to 12, this equation, dt is this equation at the top of the slide. dt is 2L by RETS. So RE less than 2L by DTS, and the maximum value of dt can be 1. Okay, it cannot be more than 1. So if you can ensure that RE is less than 2L by TS under all operating condition, then we are ensuring a CCM in all throughout the AC cycle. Okay, but again, as I told you, what I was discussing a few minutes back is that RE is indicating how much the converter is loaded. Okay, so if the converter is heavily loaded means you are drawing a lot of power out of the converter, suppose to the server. Okay, heavily loaded means low RE. Okay, low resistance, low output or low equivalent resistance, emulated resistance. Okay, so then the magnitude, if low RE, so this is the low RE value. Okay, so this is low RE value, and high RE value is this one. So this is the high RE value. Okay, high RE value means lower power, which is being, so then we call it the converter is lightly loaded. Okay, so yes, this was what I had explained in the previous slide. Now let us take an example, okay, and try to understand how the this thing works. So first question here, if you see that we are trying to charge a 400 volt battery from the single phase boost PFC. Okay, now initially the battery is drawing 500 watt from this 110 volt 60 hertz supply. Okay, the converter uses an inductor of 50 microhenry and switches at 500 kilohertz. Now this 500 kilohertz is, I think it is on the little bit on the higher side, but it does not matter here. We can also do the same analysis using a 200 kilohertz or even 100 kilohertz boost converter. But let us understand the principle and through this example. Okay. Now, the first question is, what is the value of the emulated resistance? Okay. So this we know, right? We have seen already. RD is basically the power is V squared by RD. Okay, V RMS squared divided by RD. The power is given as 500 watt. So this is the power here. Okay, and we have the voltage which is equal to 110 volt here. So the value of RD is 24.2 ohms. Now the next part is 12 by, so we have to see that whether RD less than 12 by TS is happening. This is the condition we want to test. So the value of inductor is given, which is 550 microhenry. So 12 by TS, and what is TS? TS is 1 by TS is basically equal to 1 by 500 kilohertz. Okay. This is TS. And when you substitute this one, this value comes out to be 50 ohms, right? So therefore, since RE is less than 12 by TS at all times, so the converter will operate under CCM throughout one cycle of the AC waveform. Okay. So therefore, the second part of the question is the converter working in CCM in one full cycle? Yes, it is working in CCM in one full cycle. Next question. Okay, now what we are asking is that suppose the battery is now charged at 200 watt. Okay, now how can this happen? So if you see how the battery charging happens, so there are two types of charging mode. One is called the CC mode and one is called the CV mode. CC mode means constant current charging and CV is the constant voltage charging. Usually the CC mode and CV mode of battery charging is dependent on the state of charge of the battery. Okay, so when the state of the charge of the battery is less than a certain value, for example, if the state of the charge is less than 90%, we say that we will go with the CC mode. And then when the state of the charge is more than the 90%, we go into a CV mode. Now the power consumption in the CC mode and the CV mode may vary actually. Okay. So the whole point here, what I wanted to discuss is that when you charge a battery, the power consumption or the power taken by the battery for charging purpose, that power is not constant. It can vary. So it can be 500 watt initially, but it can go down to 200 watt at the end of the charging. So now let us take the condition that this same battery of 400 volt is now uh, charged with a power of 200 watt. Okay, you are going to use the same boost PFC which you have already designed. Okay, and so the inductor is 50 microhenry and the switches are again switching at 500 kilohertz. The question now is, will the converter be working in CCM in one full AC cycle? So then you have to do the same expressions, find out these same expressions once more and find out whether that condition of CCM is satisfied. So we find out what is now the RE. Okay, you have this power, this is the power here, and you have the voltage, which is here V square by RE. Now RE is equal to 60.5 ohms that you get. You again do the same value, find out 12 by TS, and it is coming out to be 50 ohms, right? Now you see that the in order to work in CCM, right? In order to work in CCM, the original equation was RE must be less than 12 divided by TS into 1 minus VGT by V. Okay, this we had gone in, we have seen in one of the previous equations. Okay, a special condition of this equation is when dt, maximum value of dt is equal to 1, which we took in the previous slide. Okay, but now what we are seeing is it will partially operate in CCM in one AC cycle. Okay, because this is the this expression is what we had started with. Okay, so therefore RE is less than 12 divided by TS into 1 minus VGT by V. This condition must hold true. Okay, now, so if you put the values here, so 50 divided by 1 minus VGT by 400 should be true. Okay. Now this value, so therefore this RE of 60.5, so 60.5 should be less than equal to 50 by 1 minus VGT by 400. So this condition will hold true. Okay, this has to be hold, this must hold true for CCM. Now this will not happen throughout the whole, all values of VGT, right? For example, it will not happen when when VGT is very less. Okay. For example, suppose you take VGT equal to 1 volt. Okay. So you take this one as say 10 volt. Okay, 10 volt. When the value of VGT is 10 volt, because VGT is changing, it is going from 0 to 110 root 2 and then again coming back. So this is the expression of VGT. Okay, please note that this is the expression of VGT, and here at close to t equal to 0, you may get a instantaneous value of VGT as 10 volt, right? So therefore, if you put 10 volts here, you will see that this condition is violated. So which means that CCM will not be happening as long as VGT is some low value. Okay. However, what will happen here is once VGT crosses a threshold value, and this threshold can be obtained from this equation. Once VGT crosses this value here, 69 volts around, then we will go into CCM. Okay, so this shows that sometimes the converter is working in CCM in within one AC cycle. Sometimes it is in CCM, but sometimes else it is either in CRCM or in DCM. Okay, this shows that thing. Okay, yeah. So therefore, that's what I have concluded here in this one. The converter works in CCM only during larger values of VGT, where VGT is less than more than 69. and near zero of the cycle, the converter is working in DCM. Okay. Now let us look a little bit carefully into what is the boundary, okay, of operation, that is the CRCM, because many times the boost PFC, okay, operates at the boundary of the CCM. Okay. Uh, Now here uh, we are showing you a waveform in which the boost converter is working at the boundary. What do we mean by boundary? The boundary operation means, you can see here, this zigzag current, this current here, this current is the inductor current. Okay, this is the inductor current. The average value of the inductor current is this one. Okay, this is the average value, the red one, while the peak value is the purple one. So this is the peak value of the inductor current. Okay, but the instantaneous value is this current here. Okay, this is the instantaneous value of the current. Okay, now what is happening here in the CCM mode, you can understand that the current is coming to zero at the end of the cycle. Okay, in CCM, if it was a perfect CCM, we would have seen a current which was something like this. Okay, this was in full CCM. Okay, we are not doing full CCM, so let me erase this one. We are not doing full CCM, so we are basically doing a basically we are doing a critical conduction mode in which the current is going from, so it is starting from zero, okay, and it is ending at some peak value. Okay, starting from zero and ending to a peak value. Okay, now you can understand that in this way we are actually fully utilizing the inductor. Okay, the energy of the inductor, because here at the start of the cycle, or throughout when the inductor is charging up, we are pumping in energy into the inductor core, and after when it is discharging, we are fully taking out the energy from the inductor core. Okay, so in this way we are actually utilizing the full of the energy storage capacity of the inductor. Okay, we are fully discharging right now, but the problem here is as follows. Okay, but you see, so this is the critical conduction mode, but there is a challenge here. Okay, what is the challenge? The challenge is that the peak current in the inductor is increasing for the same average value of the current. Okay, now remember the average value, this one is the average value, the red one. So let me write it down in there. This is the average value. The average value of the inductor current in one cycle. Okay, the average value, remember, it is constant. It is determined by the load. Whatever the load demands, the average value of the inductor current will follow that one. But in case of CRCM, okay, the peak value of the current, okay, because this is coming to zero, the peak value of the current here must be double the average value, because we are going to take the current to the double the average and then come back to zero. Only then the average value is something which is shown in the curve. So here what is happening, the peak to peak ripple is must be double the average current. We must go to 2 times the average current and then comes back to zero, right? In a switching cycle, right? So, but on the other hand, when you had a CCM mode, you can see here what is happening. If you had a CCM mode, of course, the current was like this. This was the current which was in the CCM mode. Okay, now you see here that the peak current here is not twice the average value. Okay, it is much less. We'll have an example. We'll show you an example later. It is much less, right? So one of the things is that in critical conduction mode or even in DCM, the size of the inductor can go down because you are not storing the full energy. You can reduce the size. But the peak value of the current which is flowing through the inductor in CRCM is higher compared to CCM. Okay, so you can find out here how much is the delta IL, which will be 2 times IL. IL here is the average value of the inductor current. And so this will be 2 Vg by Re. Okay, and since VGT is equal to LDL by T on, so here is the T on time is this one. So this actually comes from the control, but we can assume that this time is T on, which is half. We can roughly assume that this is half than the TS time period or somewhat closer to that one because it depends on what type of switching we use. But anyway, if we take it T on, then L is equal, which is half of the TS time period. Then we will say that L, the value of the L will be R into T on by 2. Okay, just substituting in this value. So what I want to say here is that the in case, okay, let me see where is the example. Okay, we will take it up in an example. But what I want to say here is that the inductor value will decrease in CRCM, but the size of the inductor may not necessarily go down because the current which is flowing through the inductor is now double the value of what was there in CCM. Okay, when the current goes double, of course, you can say that, yes, I have reduced the size of the inductor, but this increased value of the current, okay, remember, this is the peak value of the current which is flowing not only through the inductor, it is going to flow through the switches, it is going to flow through the diodes, right? Everywhere, this peak, instantaneous peak value of the current must be flowing. So it may actually um, so the inductor should not saturate at that value of the peak value of this current. Okay, so not only in the inductor, but also we have to take care of the switch rating, the losses in the switch, losses in the diode, and all other wires and these things. Okay, so therefore, what I want to say here is that the when you move into from CCM to CRCM, then the value of the inductor, this value here, L, will go down. Definitely, it will go down. But it may not always necessarily imply that the size of the physical size of the inductor will go down and the losses of the overall converter will uh, decrease. Okay, it may not be. Okay, so we have to be very careful and do some rigorous analysis. Often we do it through simulation. That what is the optimum value? Okay, we'll come to this through an example sometime later. But I just want to then look into the other side. Okay, the basically the output side, the capacitor side. Okay, now um, if you look, so we have done the analysis from the inductor side, but now we'll talk about the capacitor side. Okay, so here is the capacitor. This is the place where the place where the capacitor is discharging, and this is the place where it is charging. Okay, right. So the as we have said, the instantaneous output and input powers of the converter are not same. Okay, what is the instantaneous input power? The instantaneous input power is something like P in equal to Vm sine omega t into Im sine omega t, and which has a steady DC part and a 2 omega harmonic ripple. Okay, so this is the instant input power. Okay, so this goes like this. Okay, yeah, it's a double frequency. This double frequency power is inherent. Okay, you cannot stop this from happening because of the voltage and the current. Okay, so we have to make some arrangement. But the output power, on the other hand, if you see, the output power will be constant. Okay, we would like to have the output power to be constant because we are setting up a DC voltage output. Okay, now, so therefore, the element that actually absorbs this difference of the powers between P in and P out, right? That uh, power must be, what I should say is, must be absorbed by some element, okay, in the current, and it is usually done by the capacitor. So, but the average value, remember, the average value of input power and the output power is must be same, okay, because that is what is being absorbed from the grid and it is being delivered to the load. And that also makes sure that the capacitor voltage is not rising up or rising down. Okay, average value of input power must be equal to average value of output power. But the instantaneous powers at the input and output will not be equal. And hence, the capacitor must store and release this instantaneous difference of energy which is coming at the input and the output. Okay, so which will, of course, therefore, the capacitor must be designed to absorb this difference of the active power. Okay, so with this understanding, let us see, yeah, what happens on the capacitor is that, so therefore, the instantaneous power is the difference of P in and the P load. And of course, this will cause a ripple in the capacitor voltage because any energy fluctuation on the capacitor, that will cause a change in half CV square. Okay, V being the voltage, instantaneous voltage on the capacitor. So therefore, on the voltage, we have seen here that you see in the output voltage, there will be a ripple, okay, on the voltage. Now, if you properly design your capacitor, then this ripple voltage is very small, okay. It may be less than 1% or less than 1% of the output voltage, but definitely it will have some ripple on the output voltage, okay. So, but again, as I told you, the P in, the average values, these are the average values. So let me just take a different color. So these two powers, these are the average values. Okay. Average P in and average P load must be equal at steady state. Okay. Because otherwise you are going to continuously increase or decrease the capacitor voltage. Okay. So therefore, from the control point of view, monitoring this capacitor voltage is very important, right? Because the controller ensures that you always monitor the capacitor voltage accurately so that it is not kind of like continuously increasing or continuously decreasing. If that is happening, okay, then you know that the average value of input and output powers are not constant, okay, and it will lead to instability in the operation, right? The output voltage may go from this, say, 48 volt to 0, or the output voltage may go from 48 volt to 100 volt, and then the breakers have to kick in. So therefore, monitoring the capacitor voltage is important for the controller because that ensures that input and output average powers are same. Okay, now we can quickly write down some of the equations from which we can actually design the capacitors. So what we have seen here, the energy flow into the capacitor is E cap, which is basically integral of P cap into dt. And the, as you can see, the average value of the average value of this power goes to the load, and the ripple value, okay, the P load into cos 2 omega t, this ripple part will be absorbed by the capacitor. So therefore, we only take the ripple part of the uh, or the AC part of the power, okay, that will flow into the capacitor, causing the voltage to vary. Now we will try to find out how much is the capacitor voltage fluctuation due to this energy flow into the capacitor. This is what we are trying to now find out. And so half C V1 square minus V square is the energy which is um, changing, and this will be, we will integrate for the entire time period. Note that the variation of this power is something like this, right? So this is the uh, P, P which is flowing through the capacitor. This is this equation, P load cos 2 omega t, right? So it will look like this. So which means that it is like this. So the total energy that is flowing into the capacitor is this one, right? And this will happen, right, for from t by 8 to minus, so this and minus 2. So we are trying to find out the entire energy in inside, or the area under the curve for this sinusoidal function, okay, of p, okay. The total, this is the entire thing, this part will be fed into the capacitor, the entire part of this, right? This will feed into the capacitor, and we are trying to find out by this integral, okay, here. And this will cause the variation in the capacitor voltage. Of course, we will take out everything in the this part, okay. We will take this thing out from the capacitor, we'll take out the energy, right? So therefore, this variation will cause these voltages to vary from V1 to V2, right? So the V1 and V2 are the initial and final voltages of the capacitor, and where omega t is equal to 2 pi, and you substitute this equation, half C V square minus V square is, you can write it, A square minus B square is A plus B into A minus B. And so we can write it like this way, and then we can assume that V1 plus V2 is almost equal to 2 times V, because the ripple is usually very small. And so we can substitute and can write C equal to P load by omega V square into delta V by V. Okay. So this, so delta V by, we have written it in this format, delta V by V, because sometimes we say that delta V by V is 0.01. Okay, delta V is the fluctuation in the capacitor voltage. This V1 minus V2, this is the delta V. Okay, this is the delta V. Okay, and so we can write it like this way, right? So, yeah, so this equation, equation number 20, can be a useful equation for designing the capacitance value, capacitor value. So let us look into one design problem, okay, which we have covered, all the theory we have covered, but we'll just try to see a little bit of this inductor and capacitor design, okay. So here we will only concentrate on the capacitor and inductor design. We will not go into all the details of taking the switches, diodes and all, for which there are several literatures and lectures available. You can see this one, but we will specifically focus on designing the inductor and the capacitor. So here, suppose we are making a PFC, boost PFC for a universal input, which means 85 to 265 volt AC and 50 and 60 hertz. Okay, this is the universal input. The output voltage is 400 volt DC. Okay, in many applications in single phase converters, the output voltage is kept at 400 volt, from which we have generally another set of DC-DC converter which can take it to some other voltage like 48 volt or 72 volt. In many applications, this happens. For example, in telecom power supplies, we have a boost PFC at the beginning, which takes from voltage of so this you can see in the internet telecom power supplies, which is a very popular application where you have this kind of an input voltage, and the intermediate DC link is 400 volt. Okay, intermediate DC link is 400 volt. After that DC link, there is another DC-DC converter which steps it down to say 48 volt. Okay, which can be given to the power supplies. Okay, so this is very common. Now the here we are designing what with 1,000 watt. And the switching frequency which we are taking is 100 kilohertz, and there is also something called as hold up time. Okay, 10 milliseconds of hold up time. What does this mean? It means that um, in many cases, the power supply, there is one requirement of power supplies, is that if the grid fails for short duration, or if not the grid failing, I mean, if there is a sudden disturbance in the grid. So this happens very frequently inside the grid. The grid is not always 100% giving you like 230-volt AC all the time. There may be glitches in the grid. We do not understand most of the time as an end user, but this happens in the grid because there are several things that happen in the grid, like a fault happening or something like that. So the grid, sometimes there are glitches in the grid. One form of a glitch is that we lose the grid for certain periods of time. Okay. So like for example, half a cycle, okay, or one cycle, we lose the grid. Okay. But now as a power supply maker, your job will be to provide power to the load in spite of that glitch happening from the grid side. So one stringent condition is that you lose the grid for about half a cycle or one cycle, but still able to power the load in the absence of the grid. So this is done by this hold up time here. Okay, so what is this hold up means? It means that if you lose the grid for 10 milliseconds, here we are saying 10 milliseconds. If you lose completely the grid for 10 milliseconds, then you will be able to supply the full 1000 watt to the load for 10 milliseconds duration. Of course, this will be done by the capacitor. The capacitor is going to do this. You have an output capacitor, and that capacitor will be designed in such a way so that it will should have a sufficient stored energy so that it can provide 1000 watt output for 10 milliseconds, right? This is what we want uh, from the converter, right? So therefore we have to keep this in mind when we are designing the capacitor. This is one of the stringent requirements. So sometimes we say 20 milliseconds, sometimes we say 10 milliseconds. Losing the entire grid voltage for full one cycle is actually a very big event, right? It Many times what will happen is we will have temporary sag in the grid. Okay, like 230 volt goes down to 180 volt, but for 3-4 milliseconds, and then it comes back to again 230 volt. Okay, so this is a momentary sag in the grid. Okay, these things also happen. So, but we have to kind of like make sure that our converter, in spite of these small glitches or fluctuations in the grid, will still be able to supply the load for this 10 millisecond time, 1000 watt. Okay, so so first we will design the inductor, okay, and then we will design the capacitor. So suppose we start with the CCM, okay. We know that inductor value is higher in CCM as compared to DCM or CRCM. But we will see that lower peak-to-peak ripple current can be accommodated. This we had discussed about 15-20 minutes back. Okay, so yeah, the core losses and RMS current in the inductor decreases in CCM compared to CRCM because, as I told you, the peak current in CRCM, a critical conduction mode, or the DCM, the peak current will increase in CRCM as compared to CCM for the same average value of current. Okay, so the size of the inductor may not always necessarily more in CCM. Okay, so we must also have to do a detailed analysis to optimize the size of the inductor, efficiency of the whole converter, and the THD. Of course, the THD is something which is very important. We must remember that, because if you make your inductor current, okay, if you make your inductor current something like this, okay, if you make the inductor current something like this as compared to the situation where you have the inductor current like this, okay, if you have the inductor current like this, so you can see the blue curve. The blue curve will have a THD which is much more. Okay, when you go back to the grid side, the THD of that current is very much more higher, okay, as compared to the red one. The red one is much more sinusoidal. So we have to, when we go into the CRCM or DCM mode of operation, we must also keep an eye on what is the THD happening to the grid current. Okay, fine. So when you design the inductor, so we will just follow the equations which we have already derived. So we have seen L should be greater than RE into TS by 2 to operate the converter in CCM throughout the cycle. And here in this case, RE should be taken corresponding to 265 volt. Why? Because then the maximum value of RE we are finding out, and we are going to design the value of L which is more than that maximum value, right? So we have this RE equal to this value 70.2 ohms, right? We are taking the maximum value. 265 is the maximum voltage for the same power. And so we have this RE equal to 70.2, and hence L is equal to RE into TS by 2, which we come out to be 350, around 351 microhenry. Okay. So then if you have this one, so what is the maximum current which will flow through the inductor? The maximum current which will flow through the converter and as well as the inductor is when the input voltage is minimum. Okay. So the minimum input voltage is 85 volt, right? So at that point, the maximum inductor current will flow, and which is for the same power. So 1000 watt we are feeding from the 85 volt. So 85 is the RMS value. 85 into IL RMS is equal to 1000. And so therefore IL max is 1000 into root 2 divided by 85, which is 16.60. This is the peak value of the inductor current. Okay. So this is the 16.60. So this, if you remember, we are in CCM, we are like this. Okay. This is the peak value here. This peak value is this 16.63. Okay. Now, yeah. So sorry, this is not the peak value. This is the average value here. The average of this one, average value of this one. That is the 16.63. And so at close to the peak of the sine wave, the delta IL. This is the, so over this the delta IL will come. So what is the delta IL? Delta IL is this one here. Okay. This is the delta IL. Okay. The band of the current. Right. So delta IL is Vg into dt by L. The delta value will be, we are trying to find out the peak value of the inductor current. So if you put these values, you will get 2.39. Okay. 2.39 is the delta IL. Delta IL is 2.39, whereas the average value is 16.60. The average value is here. This is the average value. This value is 16.63. Okay. Over which there is a ripple of 2.39 divided by 2. Right? So the inductor should not saturate at this value of current. So IL peak will be 17.8. Okay, 16.63 by delta L by 2, which is 17.8 amperes. Right? So now we have taken an inductor value which is close to 350 microhenry. We can actually take a value of inductor which is less than this also. Okay, this can reduce the size of the inductor. Okay, of course, L equal to 250 microhenry, the size is expected to decrease, but this may not be always the case. So what will happen is, in this case, the converter will operate in CCM at majority of the AC cycle, but will move to DCM near zero. Okay, now we are reducing the size of the inductor. As I told you before, this will cause at the lower values of the AC cycle, close to zero, it will move into DCM or CRCM. But at higher values, it will go to CCM. Okay, but still it may be acceptable. Okay, we have to see this. Okay, the input current THD may still be less than 5%. Okay, we are trying to reduce or optimize the size of the inductor. We want to reduce from 350 microhenry to lesser value. Again, if we run it at CRCM, then from the previous equations which we have derived, delta IL by 2 is equal to IL. And so the value of inductor can be going down up to 175 microhenry. Okay. But with the penalty that the THD and the peak current will increase as compared to the CCM. We can go up to this value, no problem with it. but we have to be careful about how is the much is the THD, because at CRCM the current will become like this. Okay, so uh, we have to see this one. So now we are, yeah, if we do it with CRCM, if we do it with CRCM, then what happens is that the maximum current that will, we can now find out what is the maximum current, okay, in CRCM. So we are trying to find out this value of the current, maximum value. Okay, so that the maximum current that flows to the inductor is obtained at minimum AC voltage, so at 85 volt AC. So RE during this time, the emulated resistance is 7.225. So IL is equal to VG by RE, and so IL max is 16.63. So 16.63 is this current, the average value here, the 16.63. Okay, this is the average value, but since we are running in CRCM, therefore IL peak will be double than this value. Okay, double the average value which we have seen. So this current will be 33.26 ampere. Okay, but the inductor should not saturate at this value of current. But you see, compare this value of 33.26 with respect to what we had earlier seen. The current was 17.8 here. At the bottom, you see this current is 17.8. Okay, so you see when you move from CCM to CRCM, you had decreased the size of the inductor, but the peak current that is flowing through the inductor is now increasing. Okay, and this must be taken care of. So this peak current can cause losses in the device, in the diode, in the inductor, and so the inductor should not saturate at this value of current and like that. So when you work with CCM or CRCM, certain things have to be kept in mind. Okay, when you expect that you are going to operate in a region where they or your converter is going to operate with a wide voltage and power fluctuation, then it may be advantageous to design with CCM, okay, or to work in a major part of the cycle in CCM. Okay, we can take this one, okay, like 350 microhenry for this design. But if you are quite sure that you have a very, for example, you are making a converter only for India, where it is known that it is always 230 volt, then you can actually further optimize. You can make it uh, run at CRCM or some part in DCM like that. Okay, so the detailed analysis must be performed to optimize the size of inductor, efficiency obtained, and THD. Usually, this is done through some simulation software. We use this frequently to see how much we can optimize, how much is the current, and most importantly, we also check whether the THD is happening at different loading conditions. Okay, those things we have to see. Okay. So in fact, there are dedicated ICs available which can run the boost PFC in CRCM. Okay, if you search in Google or internet, you will find that there are many commercially available ICs. They will ensure that the boost PFC is running in CRCM. Okay, the size of the inductor goes down here. Okay, uh, so yeah, now the design of the capacitor, how do you design the capacitor is something like we get the C value is like P load is omega V into delta V, right? We have seen this in one of the previous equations from 20. And so this is P load divided by omega V square into delta V by V. And so suppose I have taken delta V by V as 0.02, 2% ripple. Then the value of C is 0.83 millifarad. Okay. But we have to also, as I told you, we have to consider the hold up time. Okay. So during this hold up time, the entire power of 1000 watts is going to be given for 10 milliseconds, right? So that will cause a variation in the capacitor voltage. And so we are assuming that it will not cause a 10% drop in the voltage. So nominal voltage is 400. And when it drops, it will go down to minimum as 360. Okay, this is what we are assuming. So with that assumption in mind, we can design the capacitor, which is 2 times 1000 into 0.01. and the capacitor voltage will not go less than 10% of the nominal voltage. And that accordingly, we will find out that this is 0.66 millifarad. And so we take the higher value of out of these two, okay, 0.83 and 0.66. So this is a way to design the capacitance value. Now, inductors can also be, instead of capacitors, of course, inductors can be used, okay, as the energy storage element. Uh, but the size of the inductor will become very large, okay, because we are now going to deal with the power, because the inductor, instead of capacitor, if you use at the output, then it has to absorb this 2 omega ripple in the power, okay. And so the 2 omega frequency, which means 100 or 200 hertz, and that frequency, the size of the inductor will become very big, okay. And so we do not use the inductors. Generally, inductors are designed for switching frequency, as we have seen in the example, okay. So like hundreds of kilohertz. And other types of converters can also be used, okay, like buck boost converter. But buck boost converter, it has a pulsating input current. Buck converter also has a pulsating input current, and it causes higher THD. Now, Chook and Sepik converters may be used, but they are fourth order converters. It's difficult to control, and so we preferably avoid the Chook and Sepik converters. And most of the times, the boost PFC is good enough. Okay. So with this, all this analysis and what we have covered, we now have covered the basic operational principle and steady state operation of this converter, and understanding all the equations and how this CCM and CRCM and DCM operation happens. We took some examples also. And next we will take up the controller part of this converter. Thank you.